Okay, good morning. Wow, good morning. Oh, that got worse. Good morning. That's better. Thank you. Okay, so calendar here again. Just to remind you, we have exam coming up next Thursday. It'll be 6:30 to 7:30 p.m. just like last time. Covers lessons 9 through 17. Covered so everything from integration by parts up to the arc length and surface area that we did on Wednesday. Today's lesson is not included on exam 1. Also, take a look at next Monday and Tuesday. You have fall break. So we'll come back on Wednesday and do a review. The exam will be just like last time, 12 questions, multiple choice, 5 choices each question, 8 points per question. And like last time, the locations all over the place again. So this is posted on the course webpage. Where you go depends on who your recitation instructor again. All right? Okay, today we're going to look at 8.3. It's another set of applications of using integration for physics or engineering kind of thing. And just to make it clear, this is not on exam 2. In physics, the word moment has a specific meaning. Most often you see it is defined as the product of a force and its distance from an axis. And what a moment does is going to cause a rotation about that axis. Okay, so that's what the word moment means in physics and in our context here specifically. Give you one example that we are all familiar with. Go to the park and you see kids play on the seesaw. So it looks something kind of like that. Right? You got some kind of plank with a balancing point, a pivot. And let's say we have a kid over here, another kid over here. So each of these two people has a certain weight, a certain mass, and a certain weight. For simplicity, let's assume that these two people have the same mass. We'll call that mass m. So the force from the person on the left is mass times gravity, right? That's the weight of the person, and it's coming down this way. Same thing with this one. There's another force, m times g. The axis of rotation is right above this balancing point here, and the axis will be coming out of the page. So we all know this is going to cause some kind of rotation in this kind of configuration. And what causes that rotation is the moment from these two people. Okay, let's say the first person is at a distance d1 from the fulcrum here, and the second person is at a distance of d2 at the fulcrum. The moment coming from the person on the left is the weight, right? Force times distance. So force from this person on the left is the weight, mg, and the distance is d1. And the moment from the person on the right is the weight times the distance from the balancing point. And in this situation here, we all know what's going to happen. We're going to have a counterclockwise rotation, right? Intuitively, we know this. The counterclockwise rotation. Because the moment from the left is bigger than the moment from the right. They have the same mass, but d1 is greater than d2. Therefore, the moment coming from the left is bigger than the moment coming from the right. Okay? And also note that this g, the gravity acceleration here, cancels out, right? Regardless of the mass on either side and the distance on either side, we know if the gravity stays constant, moment is only dependent upon mass and not really the gravity here. Okay, so that's the basic idea of moment. And let's look at a few situations where we have to calculate a moment and another quantity called a centroid. Well, let me define centroid first. And often you hear people use the term center of mass instead of centroid. They mean the same thing. And it's not the same as center of gravity. Those are completely different quantities, and they don't always coincide. So what a centroid is, if we replace all the masses with a mass with the mass of combined mass, and the location at which this new mass will have the same moment. Okay, it's best if we illustrate with this with a few small number of points here with some masses, and then you'll see how this thing works. Let's say I have three masses here. The first one has a mass of 4. The second one has a mass of 1. And the third one has a mass of 5. And the location of the first point is 2 minus 5. The second one is minus 3, 3. And the third one is at 3, 5. Okay, so we got 3 points here with different masses and the locations of these 3 points. Let's sketch out where they are. The first one, 2 minus 5, let's see, roughly here. So it weighs 4 units of the mass units and sitting at 2, comma, minus 5. The second one is at minus 3, 3. I'll just kind of eyeball that right here. M2 is 1 unit, and it's at minus 3, 3. Third one is at 3, 5. Again, I'm just going to eyeball the approximate location. Okay, so if you imagine that we got these 3 things sitting on a table, but the table can pivot. And what's going to happen here is once we let this thing start doing its thing, it's going to have some kind of rotation depending on the mass and the distance from these axes. We're going to calculate 2 moments here. The first one is the moment about the y-axis. So this tells me if I just look at the rotation about the y-axis, is this thing going to be rotating this way or that way? And then I'll look at the same thing about the x-axis. Then we'll see if this thing will rotate forward or backward. The combined of those 2 tell us what this thing is going to do. And we typically write this as capital M with a subscript y. And then the moment about the x-axis, capital M, subscript x. Okay? Okay. Now remember, moment about an axis is the force times the distance from that axis. I'm just resketching the picture we got here. M1 is equal to 4, 2 minus 5, and then M1, M3, rather, M2 is equal to 1, and minus 3, 3. Okay, same picture we had before. So first, the moment about the y-axis. Okay, the force of this object times the distance from the y-axis. Then we have 3 of these. We'll add them up. Let's go in order. The first one is the force from the first point. It's got a mass of 4, right? And how far is it from the y-axis? 2, good, right? So it's this distance that we care about. It's measured from the y-axis, so 2. This is how far M1 is from y-axis. Now the second point has a mass of 1. How far is it from the y-axis? 3, but it's to the left. So let's put in a negative 3. Left of y-axis. So negative. Okay? The last mass, it would be what? 5 times 3? Yep. Okay, so we're measuring the distance from the y-axis. This is 2, this is 3, and this we put as a minus 3 because it's to the left. Okay, now you combine all of this together, you get, what do we get? 20. Okay, so 20 is positive. This means that the moment from the right side outweighs the moment from the left side. So a positive number means if I hold this thing in my hand like that and I let it go, it's going to tilt this way, right? Because the right side weighs more. Now let's calculate the moment about the x-axis exactly the same way. The first one, let's go M1 in order again. The first mass is 4, right? What about the distance from the x-axis? Negative 5, right. It's 5, but it's below. So let's put in a minus 5 for the distance. How about the second point? What do we get? What do I multiply? 1 and 3, right. It's at a distance of 3 from the x-axis. Last one. Mass is 5, distance from the x-axis. 5, right? Right, so this is a distance of 5, this is 3, and so on. Okay, so what do we get out of here? We get 8. This means a positive mx means there is more moment from above the x-axis. So again, if I let it go, it'll tilt this way. Combined with the y, it'll tilt this way and this way. So it'll tilt like that way. Does that make sense? Okay. Any question about how we calculate the moments about the axes? Just remember, it's the mass times the distance. Technically, it's the weight, but we saw earlier that the weight eventually cancels out. It doesn't matter, so we only use the mass, typically. Now let's calculate the centroid, the center of mass. It's kind of an averaged location of all of these masses and their moments. So what we're going to do here is to place a new mass with the combined masses of the three. 4 plus 1 plus 5 equal to 10. And often you'll see the location of the center of mass written as x with a bar over that. You read it as x bar. But wherever I put it, I'm still going to get exactly the same moment as I had before. I still want an my of 20 and an mx of 8. And this time the new mass is 10, right? So I really don't know where it's going to be, so I'm going to just kind of randomly put it down. And now I calculate the moment of this one point about each axis. Let's start with the y-axis. The mass is 10 units. And how far is it from the y-axis? How far is it from the y-axis? What's this distance? X bar, right. Right? That's how far it's measured from the y-axis, disregarding the x component for the moment, just the x part for now, just how far it is from that axis. And notice we also want this to be 20, because we want exactly the same moment as we had before. So x bar is equal to 2 in this case. Same thing for the moment about the x-axis. We want to know the mass, 10. And how far is it from the x-axis? Y bar. And we want the same moment about the x-axis we had before, 8, right? So that's what we want. So this tells me that y bar is equal to 4 over 5. So here's kind of what the picture we end up getting. Here's M1. This is M3 and M2. So we saw earlier that these masses will have a moment about x and y axis we can calculate. But if we shrink all of them into one point and put it exactly at the center of mass, right here, let's say, right, this bigger mass will have the same set of moments as these three combined. So think of it as an average location weighted by the distance. Average mass, where would they be on the average? So in this case, right here. Questions? Good? Okay. All right, now it's about to get a little bit harder. Now we're going to extend this idea to find the moments and centroids of a flat plate of arbitrary shape. If you want to sound really educated, you would use the word lamina, which is a fancy word for a flat plate, a lamina. Okay, so let's look at a random shape here. Well, not random, but shapes we can describe by using two curves. So I got this really strange looking plate here. It's got a mass, right? It's got a mass, so it's going to cause some kind of rotation about each axis, just like when you had discrete points. It's also going to have some kind of center of mass, just like the set of discrete points. We would like to find out what they are. So we're going to use the same trick we've been using with this kind of problem. We will divide these into a bunch of rectangles. Just like before. And how would you calculate the mass of each rectangle? It's the density times the area, right? How big is this thing and how dense it is. So that will give you the mass of each rectangle. So density is normally denoted by lowercase Greek letter rho. What about the area of each rectangle? How would you calculate that? Come on, you know this. The height times the width. What's the height? Fx minus gx. Good. How wide is it? Delta x or dx, let's jump directly to dx, right? This is the height. And this is the width. what's the mass of the entire plate? We want all of these rectangles. Each one is very, very thin. How do you get them together? The integration. Good. Okay, now we got the mass. Okay? To calculate the moment of this entire thing, we're going to replace each rectangle with an equal mass point at the center of mass of each rectangle. So this is the center of mass of rectangle. And it's going to have distance from the x-axis and the y-axis, right? So let's calculate the moment about the y-axis for this one only. Just this, the third one I have sketched. How far is it from the y-axis? X, right? Distance from here to here, that's x. So moment is distance times the weight, distance times the mass. We just calculate the mass of that one thing. It's density, top minus the bottom, dx, right? So that's one of these plates. We want the entire plate, so we turn that into an integration, and we do integral from A to B. Here we go. Now, mx is trickier. The distance from the x-axis to the center of this one is the average between the top and the bottom. You see that? The average between here and here. Yes? See that? How would you calculate the average between the top and the bottom? Yeah, add them together, divided by 2. Good. So we do 1/2 top plus the bottom. And then the mass, same thing, right? Rho times f of x minus g of x dx. And then we integrate A to B. So this part here, let me write out what it is. Distance from x-axis to center of rectangle. And x is simple. It's distance from the y-axis to center of the rectangle. Okay, now let me clean up the formula a little bit now. That density is a constant. We can pull it out. Once again, density is a constant. We're going to pull that out. So these two give us the moment about x and the y-axis. And the mass, same thing. We'll pull out the constant rho. There we go. All right, so these are the moments and the mass. To find out the center of mass, same idea. If we collapse the entire thing into one point of equal mass, then I will still get the same moment as before. So collapse into one point, distance from the y-axis. So here are the two formulas that will be relevant for this kind of work. Okay, this is from my my, and then my mass is downstairs, m a to b, f of x minus g of x dx. mx, same idea. Right? I take my, oops, this should be I'm sorry, what am I doing? X bar, yeah. This is y bar, sorry. So that's the x component of the center of mass, my over m, my over m, and y bar is mx. So remember on Wednesday I said you'll be glad this thing is not on exam 2? Yeah, do you agree? It's not too late to put it on exam 2. That's a joke. Okay. Hey, notice that the densities cancel. What that means is that the center of mass of any shape is irrelevant of the material of that shape. That's what density tells you about. So if I have the center of mass of this piece of paper made of paper, and the center of mass of an equal area piece of metal will have the same center of mass. Make sense? It's irrelevant of what it's made of. All right, so let's try this on something. Oh, by the way, you probably know this already. Right, if I have an object like this, I want to balance that on the tip of my finger. I should put my finger right underneath the center of mass. Right? We all know this intuitively. Look, I found the center of mass right here. But if I go anywhere else, it's going to have a rotation. But if I find that specific point, then I can balance it. So that's what x bar and y bar tell you. For a regular shape, we just find the geometric center. But for irregular shapes, we have to use calculus to find it. All right, so here's one example of this kind of thing. Let's find the centroid of region bounded by, I hear you like trig, so here's trig. Did I hear it wrong? Well, I like trig, so we're doing trig. Okay, it's not complicated, it's just cosine and sine. We can do that, right? right? We can do cosine and sines. It's not difficult. Shouldn't be. Okay, so what is this shape here? It's a pretty interesting shape. First, cosine. Cosine of pi over 4 is radical 2 over 2. So cosine does this kind of thing. And sine starts at 0, and sine at pi over 2 has the same value as cosine. So we get this kind of shape. Okay, so here's my shape. How would you call this thing? What would you call this shape? I don't know. It's irrelevant. Okay, so think in terms of rectangles, and then put the center of mass of that one rectangle there. That's your target point. That's how you measure distance from the x and the y axes. And look at the two formulas. My is the simpler of the two in the numerator, right? It doesn't have the more complicated 1/2 and all that stuff. So let's calculate my first. I would integrate left to right. Density is irrelevant. We just saw that. We proved it. Now, my, we need to know the distance from the y-axis, which is x, right? So this goes in here for that x. That's the distance measured from the y-axis. Then the mass of that rectangle. Top minus the bottom times the thickness, dx, okay? So what do we get? We get, let's split this into two integrals. Okay, so here's a question relevant to the exam. This material, the exact stuff is not, but how to integrate something like that, that's relevant to your exam. So the question is, how would you integrate that one? What method would you use to integrate it? By parts, excellent. And how do you know that? Because that's what it is. No, well, remember you got these two very different parts. You have a algebraic part, a trigonometric part. So that's the kind of thing that by parts can help you integrate. So I'm not going to go through that process here, but what would you let u be? X, right? Yx. It's an algebraic that comes before trig, yes? So dv is cosine x, and etc., and etc., etc. What about this other one? Same? Okay, so I'm going to skip the details there. You should be able to do that. If not, next week we'll review that in class. This will end up getting you 1 over 4 radical 2 pi minus 4. Okay, so that measures the moment about the y-axis. This is a positive number. So this means that to the right of the y-axis, there's more moment than to the left, which makes sense. And it also tells you that if you let this thing go, it'll start rotating this way, because the right-hand side has a greater moment. Okay, now let's calculate the moment about the x-axis. So here's the formula. Right? The distance to the center of that rectangle coming from the x-axis is halfway between the top and the bottom. So the average of the top and the bottom. Average top plus the bottom. And then the height, top minus the bottom, dx. That gives me the mass. So that's distance to the center of the rectangle from the x-axis times the mass. Downstairs, same thing as before, just the area. No, this doesn't. This is not real. All right. We just want mx. I'm jumping ahead of myself. Top plus the bottom, average, right? And then the height times the thickness, that gives me the mass. Okay, take the 1/2 outside, 0 to pi over 4. Difference of squares, cosine squared minus sine squared. So you don't need to know this identity for the exam, but if you happen to know it, what can we replace this with? It's a double angle of something. You happen to know it, it's great. If you don't know it, what would you do then? How would you integrate this? This thing, right? Yes? No? It'll be on the exam. That's one way to do it. You replace this with that, this with that. Or you could also use another identity. This gives you, what the heck does it give you? Cosine of 2x. It's the double angle form, which actually, if you add these together, that's precisely what you get. Huh, look at that. Anyway, let's finish this up. Okay, so you integrate that, skip the process. It's not very difficult to do. We get, what do we get? 1/4. Look at that. How nice. Okay, just the mass by itself, that's the easiest part. We end up getting radical 2 minus 1. Then finally, we calculate the center of mass. X bar is my over m. Y bar is mx over m. Okay, so mx over m. And then my over m.